Hey guys, today I just want to go through the solutions to the lesson master from 7.6. I know 7.6 is a tough section, and it's weird because the material that's presented in 7.6 isn't really that hard, but what they're asking you to do now is use everything we've done so far in Chapter 7 to put it all together and be able to solve these problems. So this video basically is just going to be going through the solutions of the lesson master. If you're having trouble still with understanding how I'm getting these solutions, you should go back and watch the other videos that we have for this section. The big idea one, that kind of just goes through the lesson from 7.6. The factoring examples has lots of examples for given a higher order polynomial, given a couple of zeros, completely factor it, find all the roots, that kind of stuff. And then the synthetic division with imaginary numbers, that deals with, hey, if you're given a root that's imaginary, how can you divide out those imaginary factors to find the real ones? So take a look at these. It is a tough section, and we're just are gonna have to keep practicing and knocking away at these problems until we see what's going on. And it's really important that you check these out. I'm happy to help you out if you come in before or after school, but the first thing I'm going to ask you is, hey, have you watched all the videos? To make sure that you've put in the time yourself, because it's important to kind of struggle through some of this stuff and try it on your own. So let's get to these problems. So the first one, they give us a polynomial in factored form. It looks like our degree is 1, 2. This one's a double root, so 3, 4. Another double root, 5, 6, 7, 8, 9. This is a ninth degree polynomial, and they just want to list out the roots that have the different multiplicities. So the roots that have a multiplicity of 1 are going to be the ones that have no exponent at the top of their factor. So if we looked at this first factor, we have x minus root 6. The number I would plug in for x here that would give me 0 would be just square root of 6. And then over here, to get this to cancel out, I would need a negative square root of 6. So those are the zeros that have that multiplicity. And the multiplicity of 2, it looks like 2 plus I, and oh, they were a little bit sneaky with this. So 2 plus I, and then the conjugate roots theorem tells us that 2 minus I should also be a root, and it would have to have the same multiplicity. What they did here was, instead of writing x minus, they changed it to x plus. So this would be x minus 2 minus I. And then they just distributed out the negative and changed it to a plus. But that's what that factor is right there. So also multiplicity 2 minus I. So conjugate roots theorem holds true there. And then the only one of multiplicity 3 would be 9. When you plug 9 in here, 9 minus 9 is 0. And we have that third multiplicity. So those are the zeros with each multiplicity in this example. Next up, they give us a p of z here. It looks like it's a fourth degree polynomial, and it has all real coefficients. And what we learned in 7.6 is that if it's a fourth degree, then we have to have 4 roots. So what they're doing here is they're going to give us some kind of information. They tell us that 2 plus I is a 0. So they want us to verify this, to check it out. So what we have to do to verify, and also I think I mentioned in class, but I may not have, this should be a z right here. It shouldn't be an x. That's a mistake from the printing. So let's take a look here. So we're going to try 2 plus I and see if it's a 0. I'm going to use this whole slide to do that. On the next one, I'll do part B. So z to the fourth, so that would be 2 plus I to the fourth power, minus 2z cubed, 2 times 2 plus I to the third power, plus 2 times 2 plus I squared, minus 10 times 2 plus I, plus 25. So this is a really good review in multiplying complex numbers together, because we're going to have to do a lot of expanding here. So I'm going to kind of use building blocks here. So we have 2 plus I. I'm going to do 2 plus I squared right here. So that would be 2 plus I times 2 plus I. And we multiply that together, we FOIL it here, so we'll get 4 plus 2I plus 2I again, and then plus I squared. Well, I squared is negative 1, so 4 minus 1 is 3, and then plus 4I. So that is 2 plus I squared. We're going to use that a couple spots right here, and then I'm going to use it also to get to the fourth. But let's do cubed first, because we're going to need that. So cubed, I'm going to take that 2 plus I squared. So 2 plus I cubed is going to be 2 plus I squared, and then one more 2 plus I. So I'm going to take 3 plus 4I, and then multiply it by one more 2 plus I. So it looks like that'll give us 6 plus 3I, plus 8I, and then plus 4I squared. Again, I squared is negative 1, so we have negative 4 here, and 6 are 2 plus 11I, it looks like. And then if we do it to the fourth power, we'd have to multiply that one more time by 2 plus I. So 2 plus I to the fourth is going to be 2 plus 11I times one more 2 plus I. And that would be 4 plus 2i plus 22i, and then plus 11i squared, which is minus 11. So this would be negative 7, looks like plus 24i. Okay, so we have our 2 plus I squared, cubed, and to the fourth. Now I'm just going to plug those in here. So 2 plus I to the fourth, we just found out was negative 7 plus 24i. Okay, so that's our 2 plus I to the fourth. Now we're going to subtract 2 times 2 plus I cubed. 2 plus I cubed is 2 plus 11i. So we have 2 plus 11i. And then we have plus 2 times 2 plus I squared. That's our 3 plus 4i. And then minus 10 times 2 plus I. I'll just leave that like that for now. We'll distribute all of them on the next one. And then plus 25. So we're going to hope that this gives us 0, because we're trying to show that 2 plus I is a 0 of this polynomial. So let's see here. So we have negative 7 plus 24i minus 4 minus 22i, right? Because we have negative 2 and then times 2 and then negative 2 times 11i. Then we'll have plus 6 plus 8i minus 20 minus 10i, and then plus 25. Now we're going to cross our fingers and see if this works out. So let's get all of our constants together. So we have negative 7 minus 4 plus 6 minus 20 plus 25. So those are all our constants. That would be like our A. Now let's look at our i's. So we have plus 24i. That's our 24i minus 22i plus 8i minus 10i. So we should get 0 for both of those. Let's see. Negative 7 minus 4 is negative 11. Plus 6 is negative 5. Minus 20 is negative 25. Plus 25 is 0. 24i minus 22i is 2i. 2i plus 8i is 10i. Minus 10i makes 0i. So we have 0 plus 0i, which is 0. So we have proved that 2 plus I is indeed a 0. That was a lot of work, but it all paid off, and we ended up getting 0. So now, we want to find the remaining zeros of P. So before I go on to the next slide and do that, let's just think about what we've got so far. Let's use maybe green. So let's make a list of our zeros. So far, I know 2 plus I is a 0. Now, what does conjugate roots theorem tell us? Well, conjugate roots theorem tells us if 2 plus I is a 0, 2 minus I better be a 0 as well. So we have 2 zeros. It's a 4th degree polynomial, so we're missing 2 more zeros. And we're going to have to figure out what those are. So what I've got so far, and I'm going to put this on the next slide, I think, is that I know this polynomial P of z is equal to, go back to our blue, I think that's a nice color. So we know it's equal to, right now, we have x minus our first root, x minus, in parentheses, 2 plus I. I know that's true. I also know we have x minus 2 minus I. So we have 2 factors, but it's a 4th degree polynomial, so there are 2 more factors that are missing. And I don't know what those are. So to find them, I'm going to take my polynomial and divide by these guys right here. I guess I could use z. I think I'm going to stick with x, but it doesn't matter what variable you use, right? So I know that when you multiply these two together, I'm going to get some kind of a quadratic polynomial, and I'm trying to figure out what these last 2 factors are. So what I'm going to do, we have 2 options here. When I have this 2 plus I and the 2 minus I like to just multiply these together now and get a quadratic, and then I'm going to use long division. So let's multiply these together. So I have x squared, and then it looks like I'll have minus x times 2 minus I. I'm just going to leave it in parentheses for now. And then I'll have minus x times 2 plus I. And then I'll have plus, these are conjugates. So when we multiply conjugates together, we get the first thing squared plus the second thing squared. 2 squared is 4 plus 1 squared is 5. So I'll have plus 5 at the end. Okay. If you're having trouble with that, you can go back and review your notes on multiplying complex conjugates, right? When we multiply complex conjugates together, the whole point is the i's go away. So, and then we have these last 2 factors that I don't know yet. So, if we put this together, we have x squared minus 2x. I'm going to write this right above here in a different color, maybe. Let's use red. So we have minus 2x. Whoop, it didn't change colors. There we go. So we have minus 2x, and we have plus xi, and then here we'll have minus 2x minus xi. Those xi's will cancel. So we have minus 4x altogether here. I'll put that in red, that's okay. So minus 4x is what came from those 2 middle terms, and then I have plus 5. And that's multiplied by whatever these other 2 factors are to get me P of z. So what I'm going to do is divide p of z, or p of x, by this polynomial. I'll use long division, and that'll give me the resulting quadratic that I'll have to factor. So we're putting x squared minus 4x plus 5 into x to the fourth. I'm just going to use x's here. You could use z's if you want to. Doesn't matter. Minus 2x cubed plus 2x squared minus 10x plus 25. So x squared and x to the fourth is x squared. Multiply down, we get x to the fourth minus 4x cubed plus 5x squared. Subtract that whole thing off. X fourths cancel. Negative 2 minus a negative 4 is a positive 2x cubed. 2x squared minus 5x squared is negative 3x squared. And we'll bring down a negative 10x and the plus 25. X squared into 2x cubed is 2x. Multiply down, we get 2x cubed minus 8x squared plus 10x. All right, plus 10x, yep. Subtract that off. Crossing our fingers, we get 0 here because this should be a factor. So we'll see. 2x cubes cancel. Negative 3 minus a negative 8 is a positive 5x squared. Negative 10x minus negative 10x again is negative 20x. And then plus 25. Lots of 5s here, so this is looking promising. So x squared times 5x, times just 5, is 5x squared. So we have 5x squared minus 20x, good, and then plus 25. Hey, check it out, it goes to 0. That should happen because this should be a factor. They told us this is a 0, so that means conjugate roots theorem says 2 minus I has to be a 0. So when we multiply them together, we divide, and we end up with a remainder of 0. So at this point, I know p of x, changing it to x, is x squared minus 4x plus 5 times x squared plus 2x plus 5 with no remainder. So to find the remaining zeros, I have to be able to factor this, or at least find those zeros somehow. Well, it's a quadratic, so it looks like I can't factor this. There are no factors of 5 that add to 2. So I'm going to have to use quadratic formula, which I know is a pain, but it's what we have to do. We have a quadratic. We could find zeros by factoring or by using quadratic formula. And unfortunately, in this case, we can't factor, so we have to use quadratic formula. So we have a, b, and c here, 1, 2, and 5. So I'll do negative b plus or minus the square root of b squared minus 4ac, which is 20, all over 2 times a, which is 2. So that gives me negative 2 plus or minus the square root of negative 16 over 2. That's negative 2 plus or minus 4i, all over 2. So that looks like negative 2, negative 1, because I'm dividing by 2 on both of these, plus or minus 2i.